you have your box, which is preferably to be nano-coated to keep the fields inside. So if you make a hot caustic process inside, also the plastic, which is made mainly of carbon and hydrogen bonds in a specific way, still you will get kind of nano layers which are very thin. It's not visible to your eyes, but they are suitable to produce some closure for the fields. Then we use the inside, we use such a zinc plate, and we use a sorry, let me change that color. Oops. You have the nano-coated copper plate. Then you have your saltwater environment. You have here water and sodium chloride. And then you have your connections. And let's say you use an LED for reducing the currents. So what happens here? Once when you put the two metals of different kind into a salt environment, into salt water, you will find that there will be a little voltage in between. And this little voltage used to be some 0.5 volts up to 0.9 volts. It depends on the quality of your nano coating and the concentration of salt. But anyway, it will appear the voltage here. So you will get some electric current which will go through the wires on the top and inside through the ions of the water. So you will get a current here. So if this current is not limited by the LED or other load which is in the circuit, in that case this current will have a stronger effect to dislocate such particles of zinc, which will tend to travel to the copper, and on their way they will combine with the oxygen ions from the water, and it will create some kind of zinc oxide. So this is why you get zinc. Now let's go back to the basic condition without these currents. What happens in plasmatic terms? If you have copper in a metallic bond, you have the atoms in a tight connection. They are very tight, they are very close each to the other. So they do not emit too much fields around. The fields are mainly inside. So when you make a nanostate, a nanolayer, what you will get, these atoms will get at a higher energy level, and they create a bigger spacing in between, while there is the interaction of the fields of attraction and repulsion repulsion between them. So they get a little more space. And implicitly, such a nanolayers will emit into the space more fields. So you'll have here fields all around, which are coming from this nano-coated copper plate. So this is what makes the magic. The fields created by these nanolayers. So now we need to evaluate or to measure the strength of the fields. So a good indicator is the mass number, not the atomic number, but the mass number, or atomic weight, in other terms. or molecular weight, or and so on. You get this mass number from the periodic table of elements. It's the number with a bigger value. In case of copper, it says it's a 64. Actually, it's copper as a metal. Actually, copper is made of different isotopes of copper. What does it mean, isotope? Iso, it means uniform, and topos in old language, Greek, old Greek means position, location. It means isotopes are the elements which are located into the same box in the periodic table. And that's made based on the number of protons. So isotopes have always the same number of protons for an element, but the number of neutrons is different. So in case of copper, it is in nature never copper 64, but it's a mixture of isotope 63. So the number of its electrons and the protons added together is 63. And you have another part of the composition of the copper from nature as a metal, which is isotope 65. Usually we have about 69% or 71% of isotope 63, and the remaining 29% is isotope 65. What you see in the periodic table of elements as 64 is just an average number. So in your copper plate, there is no isotope 64. It's a mixture of isotope 63 and 65. So you have to understand that you are working with a spectrum, with a range of field strengths. It's never fine-tuned only to one. And we have learned from the previous lessons that when you have two fields or two magnetic arrays of the same or near similar strength, in that case, these will get entangled, and they start to interact each with other. So this is the reason why these isotope 63 and 65 are hold together, because they have a near strength. So now when we go on a nanostate, a number of the neutrons will get the magnetical and gravitational fields got in balance. So all will lose from its mass number. So in case of a nanomaterial, we have such a strength, something between 58 and let's say 60. We say an average of 59. So this is needed to understand why we use this figure. So in case of the nano copper plate, we have a field strength here around, which is a field strength of around 59. But in the same time, we have some fields of the zinc plate which do not extend so much in the space, but still they exist. And zinc has an average field strength of 65. Actually, it goes from 62 to 70 because zinc in nature, it's a mixture of 5 isotopes. You can look up in Wikipedia for the article Isotopes of Zinc and you will learn more. But we use these two figures, these two numbers for the field strength. So here we have a field of 59, which is filtered by a field of 65 in this plasmatic condition. So if these will interact, what will be the strength of the leftover fields, which will be free? So 59 will interact with 59 out of 65. They'll get in a balance, and they will be left a difference of these two, which is equal of 6 or around 6 because of the isotopes. It's a plus minus of some numbers. So from these fields, we will get field strength of 6, which will manifest itself here. And if you look at the periodic table of elements, we find that carbon has 6 protons, 6 neutrons, and 6 electrons. So this field strength of 6 will pull the fields of the 6 protons of the carbon. And if you pull its protons, its neutrons will come too. Like if you pull somebody by his left hand, probably his other hand and his body and his feet will come too. Is it so? So what we create here, it's a condition of fields which manifest an attraction of a field strength of 6 or around 6. So we pull from the environment plasmatic fields of the value of the carbon. So carbon comes here in between. Now, because we have here this salt water condition, salt will allow the manifestation of those fields in a matter form. So you'll get there that carbon. Meanwhile, the water contains that oxygen here, and that oxygen will combine with the carbon, and so you will get a CO2 in form of gans, which goes down. Of course, in the same time, you have also other conditions that zinc also gets into that water. I explained before, because of this electric currents, and also because of the field attraction, because 59 of the copper, it's near enough to 65 of the zinc, so it will also pull the fields of the zinc too. So that's why what you will get here in a gans will be a mixture of gans of CO2, gans of zinc oxide, and probably some CO2 and zinc will combine, and you will get a zinc carbonate or whatever. So from chemical viewpoint, you will have a mixture of a pure element. Now, by adjusting the conditions, you can refine this a little bit better. For instance, if you don't want zinc to get into the composition, you may try to get a plastic bag. I mark it with green. You put in a thin plastic bag the zinc plate, and you have to find the right salinity and the right distance between the plates to still have the interaction, because now it's filtered also through the plastic, but that thin plastic will not allow the zinc to dissolve into the water. So in that case, you will get less zinc oxide and more CO2. Another way, if you want to get any copper which may dissolve into the salt water, you can try to do, just a second, let me clear this. You can try to put your nano-coated copper plate outside of your container of water, or try to nano-coat the zinc also to strengthen its fields, and to put outside of the box that one. But these are the things which you can experiment and bring further those principles which you learn here. So I hope you understand about why the difference of the fields, of which at least one, it's a strong field which goes deeper in space. You can feel it at meters, which comes from the nano-coated surface. Why this difference of fields manifest in to certain conditions? So let me add some. Yes.
Well, you answered the question that Herbert had in the chat here regarding the flow of the plasma and the plates and so on. He mentions that was just answered by Shandor, and as well as in the live stream, there was a question about dimensions of electrodes and the current, and so on. He says it's no longer the case. I understand, and thank you.
So here the purpose is to reduce this current to be of the order of milliamps or microamps or nanoamps. To understand the importance of these currents, so look at the living bodies, plants, animals, the body of man, for instance. You know, from labor safety teachings, that a current of 3-4 milliamperes can cause the fibrillation of the heart. So milliamperes are already too high for the living bodies. And here we replicate processes which are in living bodies, like in the living leaves. So we have to go to currents of the orders of microamps and eventually to nanoamps.
And this is why it takes a long time to make the CO2, and people must be aware that you must have your boxes going for a long time to get a reasonable amount of CO2. It doesn't come off in a few hours.
So yes,
how much is a long time?
It depends of your patience.
My boxes
Some
go
people
for
5 minutes is long, for
months.
some 5 weeks is fine. So allow at least 1 week. Of course, as soon as you make your CO2 kit, if you made it proper, you have a lot of gans in the first hour, but understand that that may be mainly such as zinc gans of zinc.
And it depends, Sandor, where you live, because we live out in a rural area, in a sort of almost like a foresty position, and we only a few in the house, and the air is very clean, so we get very little CO2 floating about, and so our CO2 production is very sparse. And Mr. Kesh has already told me to go and stick my CO2 box in the hen house with all the chickens to breathe on it, but I don't think I will, because I don't want chicken poo in there either. But so if you're in a dirty city, it actually helps.
Yeah, and by the way, you know, those soda bottles, they were in a fashion in the 70s, maybe in 80s. But
yeah, I remember those.
Still you can buy those carbon dioxide cartridges. So if you manage to take only the gas from it and to let that gas to go here in the middle, for instance, you have a small disperser, porous disperser like for fish tanks, to allow a stream of carbon dioxide, probably you can accelerate the process. And of course, it's different if you are on the top of a high mountain and in that fresh air on Himalayas, and where you have very little CO2. And if you are in a huge city like Beijing, for instance, where you have too much CO2.
Mr. Kesh has also explained that your isotopes of the CO2 can be different in different places of the world. So your C6 might be different. You might have a C9 sitting, you know, on certain places on the planet. So you might not pull in as much as what somebody who's got this correct CO2 isotopes in their area.
So absolutely. So probably you will have a different kind of CO2 from a oak tree and a different one from a palm tree.
What people must realize is if they make a lot of CO2, and I took this on board very early with Mr. Kesh saying that you need many field strengths of the CO2 to connect with the body. And so every time I make CO2, I put the new batch in with all my older batches and I create a soup pot of CO2. And so that it's got many fields that you've created over many different seasons and, you know, the different heat of the day and cool and what have you. And that all adds to the different field strengths, which helps to connect it to the body.
Yeah. Yes, sure.
What about covering the CO2 box to protect it from dirt or dust?
If you think to cover it with a sieve, which allows the air to go through.
A sieve or a cloth.
You know those old voile curtains that we used to all hang in the 80s or something like that. You know.
So probably you don't want to cover it fully, because if you cover it with a top, with a lid, so how you expect the carbon to get in? But you can get such a thin sieve. Oh, let me stop that